I'm Dave Martin, ICFRC President and host for today's program. ICFRC hosts community programs to address topics of international interest. We thank our members, volunteers, and interns for making these forums possible since 1983, and that was the year that the first flight of the U.S. Space Shuttle Challenger took place. I want to acknowledge our university and community supporters, the University of Iowa's international programs, the University of Iowa's honors program, the University of Iowa Center for Public Policy, and the Stanley UI Foundation Support Organization. And I thank today's special sponsors, Midwest One Bank, Alan Swanson, Blank & McCune Realtors, and Conrad Schultz. We also thank City Channel 4 for professionally recording our programs for cablecast on City Channel 4 or 118-2. And we also thank the UI Library's digital archives. Over 220 ICFRC podcasts can now be found on iTunes. I know many of you are familiar with Don Gurnett, but I want to give you a little bit of his background. He started his science career by working on spacecraft electronics design as a student employee in the University of Iowa Physics Department in 1959. And after completing his BS in electrical engineering at Iowa, he transferred to physics, where he received his MS and Ph.D. degrees in 1963 and 1965. He spent 1 year from 64 to 65 as a NASA trainee at Stanford University and was appointed assistant professor at the University of Iowa in 1965, with subsequent promotions to associate professor and to professor in 1968 and 72. He regularly teaches both undergraduate and graduate courses in physics and astronomy. Among the awards he has attained are the M.L. Huit Faculty Award for Outstanding Service and Dedication to Students at the University of Iowa in 1990, and the Iowa Board of Regents Award for Faculty Excellence in 1994. Don specializes in the study of space plasma physics and has participated in over 40 spacecraft projects, most notably the Voyager 1 and 2 flights to the outer planets, the Galileo mission to Jupiter, and the Cassini mission to Saturn. He is the author and co-author of over 650 scientific publications, primarily in magnetospheric radio and plasma wave research. He has received numerous awards for his research. In 1998, he was elected a member of the National Academy of Sciences, and in 2004, he was elected a Fellow of the American Academy of Arts and Sciences. Please join me in welcoming Don Gurnett.
Okay, thanks a lot for that introduction, which is probably a little too long. I'd like to have the time to just speak. Now, when Ed Zastro contacted me about, this was the second talk I think I've given to this organization, he asked me what topic I would like to talk about. And since this is the Iowa City Foreign Relations Council, I thought maybe I should talk about life in the solar system, aliens. Potential aliens at other contracts, so you would be looking forward to future developments. Now, this is also a topic that appeals to me. I'm not an expert exactly in this, but I have published in this subject. Now, I don't know what made that happen, but okay, they say it's okay back there. So if you go to the next slide, somebody's moving the slides here. Let me remind you, if you don't know this already, but Earth, our beautiful planet, is the only place where life is known to exist. And as far as the scientific topics of research, the origin of life, how life began, and how extensive it is a question that I'm sure many people have thought of, and it is now a specific scientific objective of NASA. Its top objective is to search for life, for example, at Mars, I'm going to talk about that a little bit. Next, why don't we go to the next slide? Let me just make a couple comments about the conditions required for life. It's pretty general. You can look up various books and articles on this, that there are 4 conditions that most people will agree has to be present for life to exist. A moderate temperature. I was kind of on the limit of that sometimes, I think. Liquid water. Water is the solvent for all living things. If you don't have water, life can't be sustained. Hydrocarbons. It's generally believed that what we know of life here at Earth is based on carbon. Now, that isn't for certain. There have been people that have suggested silicon and some other possibilities. So I just list hydrocarbons there. And living things need energy source. I mean, without some kind of energy, you just can't, a microorganism just can't function. So if you go to the next slide, let me talk about temperature. This slide shows the temperature of the various planets. Temperature over here in degrees Kelvin, that's with respect to absolute zero, which is widely used in science, as a function of the distance from the sun. And these are powers of 10, so 1 right here, that's where the Earth is at. 1 astronomical unit, that's what we call that. And it goes out to 100 here and 1,000. Now, you might wonder what the temperature should be at these planets. And that's fairly easy to work out on the basis of what we call a black body temperature. A black body is kind of an idealized object that absorbs and re-emits the same amount of radiation. And you can, from straightforward physics, come take a physics course someday, you can show that the temperature drops off here as 1 over the distance from the sun. And, you know, this is a very kind of obvious thing. The farther away from you are from the sun, the intensity decreases, and so the temperature has to go down. And now I shaded a region here, which is often called the habitable zone. You can suggest numbers to me, but at least at Earth, you don't find living things above about 50 degrees centigrade. Now, the centigrade scale is over here, and that's 0 degrees centigrade. The freezing point of water is 273 degrees Kelvin. And you might just pick numbers here. You can do this game yourself. But the highest temperature I've assumed here that something could live is about 40 degrees centigrade. I mean, that's getting to the point where now there are extremes that go beyond that, but that's just kind of a reasonable number. And then as far as negative temperatures, minus 60 degrees, it's amazing. You can go down to the Antarctic where they have temperatures like that, and you can, so I'm told, scoop up some sand, bring it back home, warm it up, pour water on it, and there'll be living things there. It's pretty astonishing how life is just spread throughout the Earth in such an extreme amount. So the orange line there is the predicted temperature for a black body. Now, the real temperature of the planets is slightly different than that. As I'll talk about in just a few minutes, we have here on Earth a greenhouse effect caused by water vapor, and that raises the temperature of the Earth above this black body temperature by about 25 to 30 degrees in that range. So you'll see Earth here is slightly above the orange line, but the rest of the planets, and I do count Pluto as a planet, I'm expecting cheers for that. The rest of the planets pretty well follow the orange line. If you're careful, note Venus is an oddball, and I'm going to come back and talk about that in just a minute. Let's go to the next slide. Venus, our sister planet, almost exactly the same diameter of the Earth, just an accident, but it's just very, very close. It's a little closer to the sun. It's at 0.7 AU, That means it's a little closer to the sun. By the way, right now in the morning, if you get up before sunup, you can see Venus, a very bright object. It's the brightest object in the sky except for the moon under certain circumstances. You can't, how many people have seen Venus? I mean, most people know where Venus is at. Now, Venus, our sister planet, is covered by clouds, and you can't see the surface at all, even though there is a surface there. It's still ringing a little bit. I don't know who's taking care of that. But now I have a book here which I forgot to get out of my briefcase, so I was going to use it as a stage prompt up here. This book was given to me. It's called The Real Book of Spaceflight, and it was given to me in 1952 by my parents. And that's before the space age, and I was 12 years old. And that was one of my favorite books because the first half of the book was about rockets, and the second half of the book was about the planets. And go to the next slide. Here's a page out of the real book about space travel, 1952. Venus is a young planet, probably covered by hot swamps, you know, I mean, it's a little closer to the sun and maybe kind of like the Amazon down there, raining all the time and that sort of thing. Young planet, probably covered by hot swamps, teeming with the kind of life that vanished from Earth millions of years ago, and they show a alligator-like feature crawling around the swamps of Venus. Let's go to the next slide. Now, the first spacecraft was Sputnik 1. How many remember Sputnik 1? Yeah, I thought there'd be a lot of people here. That was launched in 1957. See if I can remember the date. I think it was October 4th, 1957. And that was really a big event in my life because I didn't really foresee it but at that time, but I ended up working in space research practically my entire life, and that was where it started. And then, of course, Van Allen had an instrument on Explorer 1, which just a few months later, on February 1st, 1958, was the first U.S. spacecraft, Explorer 1. But it took a while before we flew to a planet, and the Russians or the Soviet Union beat us on that again. Not just the first launch, but they used Venus as a target. And Venus turns out to be the easiest planet to get to. It takes some excess energy from an orbit around the moon, around the Earth, but not much. And they parachuted a probe, a whole series of probes, into the atmosphere at Venus. And the first Venera, they're called Venera, 8 and 9, went through a cloud layer, and the temperature got above 100 degrees centigrade, and they died. That is, that the spacecraft failed. So they designed special temperature, you know, like a thermos bottle to put their electronics in. And they finally reached the surface with, I think it was Venera 10, 11, and 12. And the temperature just kept going up and up and up. And when they finally touched down on the surface, I don't know how many of you are going to know this, but the temperature was, unfortunately, without my glasses, I can't read it. But it was 800 and, about 900 degrees Fahrenheit. Astonishing. That's above the melting point of lead. And so you wonder, with our, being our sister planet, why wasn't it something like here at Earth? And the answer is they also measured the composition, and the composition was 90, I'm in trouble reading it again, 98%, something like that, CO2, carbon dioxide. How many have heard of carbon dioxide before? Right, I would guess it would be everybody. And the surface pressure was 90 bars. Now, 1 bar is about the pressure here at Earth, so it has a pressure at the surface 90 times the pressure of the Earth's atmosphere. You can land a Boeing 707 at a little over 20 miles an hour in that atmosphere. But of course, at that temperature, I don't think you're going to be taking any tours to Venus, at least not yet. Almost no water. Now, next slide. Why is this planet so hot? And the answer is the greenhouse effect. I could ask how many people, but you've all heard of the greenhouse effect, haven't you? Don't let anybody tell you that there isn't any such thing as a greenhouse effect. The basic effect there is that the visible sunlight will go through the clouds. Now, the sunlight may not go straight through the cloud, but the photons kind of bounce around in the cloud and basically come out the base of the cloud layer. And that cloud layer was up at quite high altitudes. It was on the previous slide. I don't remember exactly the number. And then it heats the surface, and the surface radiates infrared, and the infrared cannot go through the clouds. It's trapped, and that builds up the temperature under the cloud layer to these very high temperatures. Now, Jerry Schnorr is here, and I asked him, I think you talk about environment, don't you? That's the thing I believe I remember that rather well. I've wondered when I see articles in the paper about the problem with putting CO2 into our atmosphere, why they don't mention Venus. I mean, if you want to convince people, these people that believe in science, of the importance of carbon dioxide, Venus is just a prime example. Now, a couple of facts that I'll tell you that I asked Jerry beforehand if he knew about this, but it turns out that, of course, the 2 planets were formed at about the same time, so you'd think they'd be made up more or less of the same stuff, and that's what people believe. And it is a fact that originally both planets had about the same amount of carbon dioxide. But here's the key difference. Venus apparently did not form an ocean. That's probably because it's just a little bit hotter, closer to the sun, and the vapor pressure of water is very sensitive to temperature. By the way, you may have seen that Ames, Iowa State University, has shown that over the last 50 years, the humidity has risen. I think it's about a factor of 2 in Iowa. And that's because the Gulf of Mexico down there, the temperature in the Gulf of Mexico has come up a little bit. It doesn't take much to cause more evaporation. And we often get a flow from the south or southwest that brings that humidity up here. So, as far as I'm concerned, that's what's causing it. Now, the carbon dioxide, this is the current belief, is that Earth, the carbon dioxide was dissolved in the ocean and precipitated out in the form of limestone. So that's where the carbon dioxide resides. Well, it formed limestone. It's not really, we don't call it carbon dioxide anymore. But I can tell you that it's a reversible process. I'm not claiming this will happen, but if you raise the temperature of the Earth enough, you can convert the limestone to carbon dioxide, which is what you have in, let's say, beer, the gas there. And you raise the temperature enough, and the carbon dioxide will bubble out of the beer or water or wherever. And if you carried that to an extreme, you would reproduce the atmosphere of Venus. So just a kind of a data point here, if you want to keep that in mind. That's probably not going to happen anytime soon. I'm not claiming that, but it is an interesting fact the 2 planets have about the same amount of primordial CO2. Okay, let's go to the next slide. I'm going to switch to Mars now. Now, I show you a picture of Mars, and obviously this is not a very good picture. This is taken with like a Kmart telescope. A telescope was invented in early 1600 and didn't really improve a whole lot for many years. And the reason I'm showing you this rather poor quality picture is that we can pick out certain features. One of them is the polar ice cap. It's just obvious. There's ice of some type there, thought to be water, but another possibility is actually frozen carbon dioxide. We now know it's primarily water, but it does have a carbon dioxide component. And then you have dark areas, kind of dark, and then kind of sand-colored areas. Now, it was observed, people noted in the 1800s that the dark areas changed as Mars went around the sun. And that led to the idea that it had vegetation, which was varying with the season. We now know that that's not the case, and I'll show you why in just a minute. The change in the dark areas is because Mars sometimes has very strong winds of 100 miles an hour or so, and it blows the sand around and reveals dark areas, and then that'll get covered up with dust and so forth. So just keep that in mind, the dark areas. Let's go to the next slide. Now, there's an astronomer by the name of Schiaparelli in 1888 made this drawing. Now, at that time, I'm not sure photography may have existed, but they hadn't had the cameras connected up to telescopes. And so he looked through a telescope and made this drawing. And you'll notice these linear features, which he has in his drawing. Being an Italian, he named those, called them canali. When that was reported in the U.S. press, the name was slightly changed to canals. Now, canali in Italian means channels. Canals in English will remind you of water in canals. And that's the way it was interpreted in the U.S. press. And there was a banker, an aristocrat in Boston by the name of Percival Lowell. And go to the next slide. He got intrigued by this whole thing of water at Mars. And he was a rich man, and he funded a telescope at Flagstaff, Arizona, now called the Lowell Observatory. And he spent the rest of his life, his retirement, looking through that telescope. And he was also a popular lecturer about all kinds of things. And he was convinced that there were water-filled canals built by intelligent beings at Mars. Go to the next slide. And he even made a drawing of all these canals, and he developed a theory, which was there were intelligent beings we call them Martians, who were in a drought, and they were funneling water down through these canals from the ice cap. And he lectured widely about this, and he had the world pretty much convinced that there were intelligent beings on Mars. And I'll give you some evidence about how convincing he was. He lectured widely. Go to the next slide. For example, in the Wall Street Journal, that's not known to be a highly liberal, speculative journal. You might even call it conservative. And they stated, I've actually looked this up, got hold of a copy of the journal down in the library, and the Wall Street Journal stated that the most important event of the year was the proof by astronomical observations that conscious, intelligent life existed on the planet Mars. Now, this led to a program in 1938 where Orson Welles, along with some other actors, had a program on a radio, and they pretended that they were reporting a very recent event, which was the landing of aliens in New Jersey. And the script followed a play, actually, War of the Worlds by H.G. Wells. And if you read an account of that, this was, of course, before I was born, has anybody here actually heard that program just, okay, I almost, when I give this talk, I almost always get somebody that actually heard it in 1938. And anyway, so they were reporting this like they were reporters on a radio. And it caused panic on the East Coast, people fleeing New Jersey. Maybe you read all this. So, the reality would suggest that, okay, let's go to the next slide. I probably have to hurry along here. I'm okay. Now, I have in my office a paper published in the Astrophysical Journal, a very well-known journal, highly respected journal, by a guy by the name of Sinton. I don't know if he's still alive or not. I'd certainly like to meet him if I had the opportunity. He studied the infrared spectrum of the dark areas on Mars. I told you about the dark areas, which they thought might be vegetation. And so he studied the reflected light spectrum and the infrared spectrum and showed that they had almost exactly the same absorption lines and general shape of the spectrum as lichen, moss, and dry leaves on Earth. And it was the existence of vegetation on Mars was regarded as absolutely certain. And notice the year, 1957. That's the year Sputnik 1 was launched. So this is where the space age began and what we thought we knew about Mars. And I remember all this. We thought there was vegetation on Mars. Then go to the next slide. It took a while before any spacecraft reached Mars. And if you look back at the history there, Mars, we just had failure after failure. There was an era where the Jet Propulsion Laboratory, the nose cone of the rocket wouldn't come off, or the thing would tumble. I mean, including the Russians, they had failures on trying to do these planetary missions. And the first spacecraft to reach Mars was a U.S. spacecraft. Finally, the Russians beat us to Venus. They also took a picture of the backside of the moon before we did. And but finally, we beat the Russians, at least in one aspect. That was to get to Mars. And this is a picture of the spacecraft, and we Van Allen, had a Geiger tube mounted on here, which is back on that side. You really can't see it. It was launched on November 28, 1964, arrived at Mars on July 15, 1965. Let's go to the next slide. And I will tell you, vivid memory of these pictures. There was a whole series of pictures transmitted back to Earth, and I want to tell you how these pictures were made. At that era, we did not have laptop computers or personal computers. In fact, they had no way of plotting a picture. And I watched this happen. They had, for each one of these frames, a big piece of paper about this big by this big, and it had little blue lines going across it, real close together, And the bit rate for the spacecraft was about 8 bits per second. And that would generate the intensity of 1 pixel on the Vidicon. And there was a guy standing in front of the paper, and they would read out the number, and he would shade in that little box with a pencil, a lead pencil, showing the intensity. And that's how that picture was taken. Of course, we have much more automated thing now. You do it all the time. Your laptop, you just push a button, and there comes your picture of your granddaughter or something. Well, we didn't have that in those days. That's somebody said, "Wow." Yeah, I look back on this my entire life and think about all this stuff, how things have changed. Now, there was another important measurement was made, and that was the surface pressure of the atmosphere. When the spacecraft went behind Mars, the radio signal had to go through the atmosphere. And the atmosphere just caused a very tiny delay in the signal, and from that they could work out the atmospheric pressure. And the atmospheric pressure turned out to be 5 to 7 millibars. I guess maybe I'm pointing the wrong direction here or something. Maybe my battery died. Probably, oh, it's still there. 5 to 7 millibars. Well, remember, a bar is about the pressure of the Earth's atmosphere, so that means it had a pressure of about 1%, a little less actually, of the Earth's atmosphere. And that has the following very important implication, because at that pressure, you cannot have liquid water at Mars. If you put a pan of water out there on the surface, it'll sit there and boil until it's all gone. And that meant that there could be no liquid water any place on the surface of Mars. And the whole idea of vegetation and things like that, you have to have liquid water. And this said, okay, let's go to the next slide now. We did land on Mars with Vikings 1 and 2. Probably people here remember that. That's more recent. And that was really a historic event. The whole idea was to land on July 4th, the bicentennial anniversary of the United States. But there was a huge dust storm, and they put the spacecraft purposely in orbit around Mars, and they had to wait until July 20th to actually land the spacecraft. And then the second one was on August 7th. But let me tell you, landing on Mars and surviving, that is, having anything but wreckage left, is very difficult. Extremely difficult. So just the other day, they had a spacecraft called InSight, came down and landed on Mars. I don't know, you may have noticed it was just a few days ago. But I'll just give you some idea of some of the problems. They use a parachute. But the trouble is the atmospheric pressure is so low that the descent rate on any reasonable parachute you can make is about 60, 70 miles an hour. So that ain't going to work. And so they have to land right at the final stage of the landing. They have to use the rockets to slow it down and come down with a very moderate vertical velocity. Worse than that, okay, to do that, you have to have a downward-looking radar that measures the distance between the spacecraft and the surface. And, of course, you got to land before you run out of fuel. So this is a very interesting engineering problem. How much fuel can you put in your spacecraft and just run out when you touch the surface? I mean, that's the idea. But it's worse than that, because sometimes the wind velocities, even in this very tenuous atmosphere, can be substantial, up to 100 miles an hour. So you also have to have two more radars, one looking horizontal and then another one perpendicular to that looking at this, to measure your transverse velocity. And you cut the parachute loose and you start the rocket engines, and you have to have feedback here that reduces the transverse velocity down to 0 for landing. So it's really very difficult, and I remember thinking this isn't going to work, but it did. And let's go to the next slide. They took the first picture from the surface of Mars, and that's the first picture came back. It just looks like you're out in someplace out in Arizona. Why don't can you back up on previously? I forgot to say something there. Yeah, there's a digger here, which I don't know if I can really, right here. This thing here is an extendable arm that would go out, and you could dig into the soil and take a sample back into the spacecraft, and they did that with the purpose of looking for life. I could go into the long story about how you look for life, but let me just summarize in the simplest possible way. You give it Campbell soup. The only thing is the elements in the soup have been radioactively marked. And then you see if there's living things there, presumably it'll eat up or ingest the soup. And normal, and the whole idea is it would then generate carbon dioxide in the process of, using up that soup, and then the gas was taken to another chamber and looked for radioactive debris, and nothing was found. So that it took about 2 or 3 years for people to decide on the basis when there were 4 experiments like that. So nothing was found. Okay, go on one more slide. Now, Viking, a lander, was taken to Mars on what we call a mothership. And that mothership was put in orbit around Mars. And then they released the lander from that ship. Now, the mothership had thousands of orbits, and they took all kinds of pictures of Mars. And they found these regions, which were craters, but they were bullet-shaped like this. And the conclusion was in these that these were dry riverbeds, and water was flowing around these craters. Now, water can't exist, liquid water can't exist at Mars, so the conclusion was that there was a much early era, probably several billion years ago, where the atmospheric density was much higher, such that water could exist. And if you had higher pressure there, you probably had a greenhouse effect, which raised the temperature on Mars. And that's kind of what we know today, actually, that there was a distant past, in the distant past, thought to be on the order of maybe 4 billion years, long time. Let's go to the next slide. Now, the issue is there must have been a lot of water at Mars at one time or other. And I got involved in a spacecraft to search for that water. It's actually a European spacecraft, but we proposed to fly a radar, a very special radar, which used a really long antenna. Can you see that antenna there is 140 feet long? And that's an interesting problem, how to get that thing in there and get it to come out. But it worked, let's put it that way. And so we made some of the very first searches for water at Mars. See, that's one of the things you need for life. So do we still have water there in some form? And let's go to the next slide. Here shows a nice modern picture taken from a spacecraft of Mars. And I'm going to focus on the polar ice cap up here. Next slide shows some of our data where we flew over the southern polar ice cap. The one I showed you was in the north. And this is an elevation plot, and it's obtained by a laser, just like I'm using here. 5 minutes, okay? And the laser is pointed straight down, and we measure the time delay for the pulse to go down to the surface and come back, and from that you can get the elevation. And here's the track right over the ice cap, and you see red, that means it's high. It doesn't mean it's hot, it's just a higher elevation. And our radar, here we pick off the surface. I don't know if you see what that is. That's distance measured downward from the spacecraft. And here's the surface. And then here's the ice cap, and you can see the top of the ice cap there. But our radar goes all the way through the ice, and we can pick up the reflection at the bottom of the ice here. And it's just been recently published by an Italian group. They've done quite a careful analysis of that reflection down there. Turns out liquid water has a very high index of refraction, and so you tend to get a very strong reflection from that. And they've concluded that that's liquid water. And that's probably because it's like a glacier at Earth. If there's some motion down there, it'll heat up that boundary and convert ice to water. But that's about the only place that I know of that we found liquid water. However, we have found considerable permafrost over a good fraction of the planet. And that means the water has, when it was a liquid water, was down in the surface and frozen in the form of permafrost. Okay, let's go to the next slide. You may have seen in the news that there have been actually several rovers landed on Mars. And this is a Curiosity rover. And its specific objective was not to really look for life. It didn't have any instruments to try to look for life, but the whole plan was to follow the water, just like the FBI follows the money. If there's living things, we want to find out where the water is. And there's going to be another lander like this flown in 2020, still another almost 2 years. And it's going to be specifically designed to look for, again, for life. Remember the Viking 1 and 2 was not a rover. It just had to, wherever it came down, it's the only place you could search. But with this rover, you can, they can go quite a large number of miles over a few years. Okay, let's go to the next slide. So the current summary of current knowledge at Mars. Mars once had liquid water and a moderate temperature, maybe even like here at Earth. That's not known. So far back in history, it's hard to answer that question. Mars is currently in an ice age, and that's because of its tilt of its rotational axis, and Mars' orbit around the sun is highly eccentric, and they're in an ice age there. Vikings 1 and 2 found no evidence of life, and we think hydrocarbons are extremely rare. Now, let me go to the next slide. Okay, now I have a story here about looking for life elsewhere, but I presume we're down to almost exactly 2 minutes. I'll try to give a crash course here and try to search for life elsewhere. Now, go to the next slide. Jupiter has 4 large satellites called the Galilean satellites, after Galileo, who first saw them in a telescope. And this one, Io, is very volcanic. It's being heated by tidal heating as it goes around the planet. However, no evidence we know of water at Io. The next moon is of great interest. It's called Europa. And go to the next slide. That's about the same as our size of our moon, almost exactly the same. And we first had the very first flyby of Europa back in 1979 with Voyager 1 and Voyager 2. And those pictures revealed a surface that was almost immediately identified as ice. And this is a picture of it. And you can see all kinds of cracks all over the place on this icy surface. Well, it took a while, but we eventually concluded that this moon has a ice layer, the thickness of which is not known exactly anyway, and has an ocean under it. Let's go to the next slide. Here's one of the pieces of evidence that there's an ocean under the ice. For one thing, you can see all kinds of cracks in the ice. In fact, if you fly out of Chicago over Lake Michigan during the winter when there's an ice layer, you can see similar cracking in the ice. And there are what we think are ice flows that almost perfectly match up here, like right there. Like the ice flows separate apart, and the water came up in between and then froze. But it carried up some other, I'll call them nutrients or whatever. And so it's not really water. It's just been discolored by I'll call it contamination in the water. So go to the next slide. Now at Earth, many years ago, I'm guessing it's about 30 or 40 years ago, they discovered these geothermal vents in the ocean. How many people have heard of it? Quite a few. And this is deep down in the ocean. Where there's no sunlight can penetrate to this depth, and there are these living things called tube worms that live off of sulfur down here. Now there are people that are smarter than I am that have studied this issue, and they think that life at Earth may have originated at these geothermal events. I'll let you research that, but that's what they say. And so the thinking is that Europa since it has an ocean, it probably has geothermal events like this. The reason is the moon is being heated by tidal heating. So, just kind of like at the Earth, the core of the Earth is producing heat and driving these geothermal events. So let's go to the next slide. Okay, so there's a very high emphasis now in NASA to go back and really research the Europa. in the ocean. In particular, the long-range objective is to put a submarine down there. Yeah, I know that makes your eyes jump, doesn't it? But that's the plan. That's the plan. The plan will be to have a radioactive heater that can melt its way through the ice and get a submarine down there in the ocean and have cameras on it and look for geothermal events and things like that. Now, before you can get a submarine down there, you got to find out the thickness of the ice. Because if it's 10 kilometers thick, we're not going to get there. If it's 100 meters thick, then we can. And we are right now building a radar, my group is. Don Kirshner is in charge of it. I don't know if I mentioned his name before, but he's the guy he's the engineer that's making it. And it's a very powerful radar, kind of like we had on Mars Express, and has a Yagi antenna. You can see the antenna there. And we're going to send radar pulses down toward Europa and measure the thickness of the ice. And don't be in a rush for this. It's going to take. It's going to be flowing in 2022, and let's see. The last time we went to Jupiter, well, there's two ways to get there. One is the fast track, which takes a big rocket, and we may use. Hasn't been decided yet. This. Let's see. It's called the ISS. Anyway, sorry, I'm having trouble putting this together because it's called the Senate Launch System. It's bigger than the Saturn V, and I believe they're talking about having the first flight of that next year. And if that works, the thinking is we're going to get there, and we could get there in a year and a half if they use that rocket. On the other hand, that rocket costs a lot of money. And another way of getting there is to go to Venus first, use gravity assist, I think 3 times between the Earth and Venus. And it'll take about 5 years to get there via that route, but it costs less money, so it remains to be seen. Okay, so that's pretty much my current. I do have in the title there to search for life in the solar system and beyond, but we're going to have to drop the and beyond there.
Okay. Well, the first question says life equals water plus air, etc. Isn't that a bit myopic to only define it as life on Earth? What other possibilities are there for life, in quotes, of a different sort that doesn't require water and oxygen?
That's a very fair question. In fact, there's a whole topic developing at some universities called astrobiology, where they're basically kind of theoretical analysis of what other life forms might exist. But my view on that is let's start with carbon-based life like we have here at Earth. At least it's a known thing that works very well. I hope that's an adequate answer.
Okay, there's 2 questions here. Will we ever have interstellar travel? And will there ever be a terraforming of Mars? Stephen Hawking says yes. Somebody says no.
Your name's Martin, is it a relative?
Yeah, I don't know. No, Martin Ross, I think.
Okay, let's see if the 2 questions. The first one was, will you ever have interstellar flight for humans? That is. Well, interstellar. I would say no, but there's always people who will call you pessimist. But I'm telling you, to fly to another star. Okay, I'll give you some rough facts. The highest velocity we can get now is about 20 kilometers per second. Voyager, via gravity assist at Jupiter, Saturn, Uranus, and Neptune, we've gotten up to around 100 kilometers per second, I believe is the number. I'm running off of memory. Anyway, I have actually computed this myself. It's going to take 30,000 years to get to get to 4 light years, which is the closest star, Alpha Centauri. And that's the closest, absolutely closest star, 30,000 years. Now, so it's clear that we need improvement in rocket performance. A factor of 1,000 would help. And I believe I can say and have support of most of my colleagues, we don't see anything at all that seems achievable to gain even a factor of 2 to 3 in the way of rocket performance, meaning velocity. I could tell you what the best idea is if you want to spend the time. The best we could do right now, I use the word gravity assist. What that consists of, you fly a spacecraft near a planet. And if the planet's moving at a substantial speed, you get a kind of a crack the whip effect that speeds the spacecraft up. With Voyager, we did that, Voyager 2, we did that 4 times. At Jupiter, and then we went to Saturn, and then Uranus and Neptune. And I believe we gained a little over a factor of 2 in velocity. Actually, it was pretty significant. It got us to Neptune instead of 12 years, instead of 30 years, it got us to Neptune in 12 years. And in terms of my lifetime, that's significant. Now, the best, just the way the mathematics works, the best way to use gravity assist is to use a large object for the gravity assist and save the last stage rocket to fire it when you're at the highest possible velocity. So the scheme is fly the spacecraft from Earth to the sun and go as close to the sun as you can. Fire the last stage rocket there, and then you can get something like a factor of 3 to 4. The variation there is how small the final stage is. The smaller, better. But, you know, that's not 1,000. That's just, and that may be done. They're talking about, I've been on a committee, actually, where we talk about an interstellar probe. Our objective isn't to get to Alpha Centauri. It's to get to 1,000 AU in 50 years. Now, right now, Voyager 1 is at 140 AU, and it's been going since 1977, and that's 51 years. So we could, so that's the best we know of. Now, there are people out there can write papers about using antimatter for the fuel and some things like that, but we don't even know how to contain antimatter, how to hold it in a tank.
So here's the question about you thought was going to come first. What's the typical budget for these projects that you discussed?
Okay. Well, I think we have a spacecraft was probably one of the more expensive ones called Cassini, which was put in orbit around Saturn. And it had about a 14-year mission there and tremendous results, in my opinion. And I think that one, counting the rocket and all the money to pay people working for 14 years, I think it's up around $6 billion. A lot of money, but there's a lot of good results came out of it. A more typical spacecraft, like you put in orbit around the Earth, like one of these communication satellites, they'll typically cost $100 million. The rockets are running like $1 million for a substantially sized rocket. Space research, space flight is risky, and all it takes is one failure of some minor component or some kind of mistake, and it's all wasted. So a lot of work is put into quality control and testing and trying to make sure that it's going to work. Those that might remember this, in the very early part of the space era, the United States had a lot of failures, and I definitely know about those. Our chances of having a rocket work were about 50%. And I mean, that's just, I have a list of all these projects I've worked on, or our group has worked on, and so forth. In the early days, it was about 50%. And then a guy by the name of Bill Pickering took over the head of the Jet Propulsion Laboratory, which we do a lot of work. That's out in Pasadena, California. And he changed the whole philosophy in the following way, that he said, if we can test it in any way before it's launched, we will do that. And that has all kinds of implications. That means you analyze every possible failure mode that you can think of, and temperature test and thermal vacuum chambers and all that. And basically, he turned around the failure rate to the point where it is now. He's no longer, I think, living. I'm not quite sure about that. But so that's been the philosophy, except for a short period where a guy by the name of Dan Golden was in head of head of NASA, actually, and he advanced a different philosophy. He said we got to save money, and that we're over-engineering these spacecraft. And in fact, I wasn't there, but I have a video of his lecture to the Jet Propulsion Laboratory engineers and people who I have the highest regard for. I just can't put. And he basically chewed us out for spending too much money. Well, if you look at the history, after Dan Golden was there just for a few years, there was a very big increase in failure rates. And when it fails, you lose all the money. And that's been turned around, especially by the human space program. I mean, if you're going to fly on a rocket, you got to have a low. And about the best rocket they have is about 1 out of like 50 launches. I think the Russians are actually ahead of us on that. They have the Soyuz rocket, which the basic design was for Yuri Gagarin, the first astronaut to go into orbit. It's the same rocket. It has different avionics, but I think it's the most reliable rocket in the world. And with the space shuttle, well, so let's see, what was the number? It was around 50, I think, and then they lost two space shuttles. So, unfortunately, space flight, as we know it now and the way we do it, costs a lot of money.
Okay, go ahead.
Okay.
Thank you. We're going to conclude our program now, and let's give Don a big thank you for his presentation. I want to again thank our sponsors, the University of Iowa's International Programs, the University of Iowa's Honors Program, the University of Iowa Public Policy Center, and the Stanley UI Foundation Support Organization for their support. And we thank today's special sponsors, Midwest One Bank, Alan Swanson, Blank & McCune Realtors, and Conrad Schultz. And we thank City Channel 4. Don, this will come as no great surprise, but as a small token of our appreciation, we'd like to present you again with our coveted Iowa City Foreign Relations Council mug. We are adjourned. Thank you.